Alrighty. Welcome everyone to the Refinitiv developer community. Today we're going to be looking at my latest article, ARMA modeling with arbitrary non-consecutive lags and exogenous variables using Python. And here we're using specifically Sympy. Sympy is a Python library that focuses on matrix algebra, actually not just matrix, but just mathematics in general. And it's very good at showing the actual maths, showing the actual variables, and it goes through Markdown and LaTeX kind of writing so that it actually shows you all the data. And that's why I wanted to use this, so that you have a very deep understanding of what's happening mathematically behind the scenes. Okay, it says part one, as I've mentioned before, because we're only going to do today the matrix mathematics and statistics. I haven't gone around to the parallel computing and the actual function building itself. I've gone through all the logic, I've gone through all the Python coding, but I haven't put it all into one function yet. This is just part one. In part two, I'm just going to update this article with all that at the very end. So that's what we're doing. So we're going to start with just the fundamentals of what an ARMA model is, just in case you don't know what it is. Then we're going to go through the estimation method. We're going to use maximum likelihood estimation. It's actually quasi maximum likelihood estimation, as you may see in the future, because we have to assume that the first few errors of our model is always 0, and that's just a little quirk to do with the mathematics. But you're not meant to use these models with too little data. You're meant to have at least 100, I'd say, observations. You don't have to have 100. I'm using daily data. If you use monthly data, it tends to be a bit more difficult, maybe 30 odd something. And it depends also on the number of variables. Anyway, I'm getting ahead of myself. Let's get started. A ARMA model is simply just one of the simplest econometric models out there, whereby I have my YT, let's say that's the stock price of a specific stock tomorrow. So let's say that T is maybe today. Let's say that T is today, and it's equal to C. Now the little C here is there to represent an intrinsic value that we believe the stock may have. Even if the company makes no profit, even if the company doesn't really function very well within its economy, it has some assets. It might have a factory, it might have some labor and things as such, which means that it has some intrinsic value. Maybe it has debts, and then you can get into the real meat of the subject. But this is kind of the most rudimentary model, really, that just looks at the intrinsic value being C in this occasion, C for constant, in case you don't know. And then we try and figure out if the cost of that, or the price of that asset, the price of that stock, let's say, is correlated with its previous day's price. So YT minus 1 here would represent this stock's price yesterday, if YT was the stock's price today, and YT minus 2 would be the stock's price 2 days ago, and we're going to go on and on until minus P days ago. And we're looking at the price of that stock, and we're saying, okay, I think that the price of that stock yesterday is correlated to today's price to a certain extent. Let's say that I think that 50% of the value of the price today is correlated to the price yesterday. In that case, I would make that little symbol, which is called phi 1, 0.5, which would be 50%. And then make phi 2, let's say the one 2 days ago, I think that's 10% influence on today's price. That would be 0.1 for 10%, and so on until P lags. And then I have an error. So my model, I did put the error in the middle, which is not a great idea. Let me go back to this error. Let's go there instead. Let's say that I had my model yesterday. I applied my model yesterday. And let's say it said, oh, today's price for the stock is going to be $10. And let's say that actually it turns out to be that the stock was $11. I undershot by $1, which means that I got an error of about 10%. Let's say that I want my model to learn from its previous mistakes. I want it to take into account the previous errors made by the model. So what this is here, epsilon t minus 1, is the error that the model did yesterday when trying to predict that model at that point. And let's say again, I think that the error of my model is correlated with its prediction today to a certain extent. This extent may be, again, let's say it's 10%, in which case that little symbol here, psi, would then be 0.1 for 10%. And you can go on like this. So this is error number 1, this is error 2 days ago, and you go up to Q days ago. Now I say day because I've chosen the frequency to be daily, but if you're looking at macroeconomic stuff, it could be monthly, quarterly, whatever your frequency is, this is what this is. It's your lag. So if it's daily, that would be 2 days ago. And you have this factor here that takes into account the errors of previous models. And what this here is the error for today's value. So if I were to know what today's, let's say, close price is for my stock, then the difference between the actual price and my predicted price by my model would be this epsilon right there. All right. I forgot to mention that you can actually find this article by going on this link right there. It's actually not on the use cases yet, but you'll be able to find it on the developers.refinitiv.com in articles probably tonight. Long story short, if you go to explore all articles, it should open up. There you go, and it will be at the top as of tomorrow. When we have a model like this, it's quite long, and it might be very difficult to understand what's going on when it's when you've got everything laid out one by one. So we'd like to maybe have everything packed up, compacted, and that's why we've got these summations. All this means here is what's there. So this here is just a summation from I equal 1 to p from everything we've got here, and we've got the same thing here for the errors. So what that summation means is this right there. And I've left the error for today's model purposefully outside because I don't want to include it into this summation. And then there's a little bit of algebra. We're taking, which one are we taking off? We're taking this one, putting it on the other side of the equation. So we're subtracting from both sides of the equation, and then we are unpacking it again, and then we're using something called the lag operator. Now, you don't actually need to know much about this for now, for this specific use case that we're looking at today, but it's good to know. I think this is called the I actually forgot. It's got a name. This specific the walled representation of the model when you have your lags in there, and you can also put it into a summation form. Now, this was a simple example of what the ARMA model is. You can use an ARMA model with as many permutations of lags as you want. So you can have p being the number of lags. If you remember, there it is. So number of days back lags we're taking for YT. So let P be 2, and Q, if you remember again, here it is, Q is the number of errors that we're looking back for in the past, and here it is. So let's say that Q is 3 and P is 2, then you can do the exact same mathematics I did right now, and then you can have a look at the stationarity of your model. Now, I'm not going to go too much into the stationarity of things. You can have a look at this online. There's quite a lot of articles out there. I've also written, this is right there. You can read this not only in this article right here, but also if I was to scroll up in this one right there, information, demand, and stock return predictability coded in R. If you Google that, it will come up. And I think if you go on part 2, that's where you have you have the same explanation on ARMA modeling, and in there you have all the things about to do with stationarity, just like we do right here. Okay, so basically what we're trying to do is to make sure that our model does not predict infinite values. If it doesn't just explode going forward. And to do so, we're going to be using Taylor's expansion. Again, I'm not going to go too much into the mathematics because everything's written right here for you. And here I talk about what a unit root is and how it's related to stationarity with an example. All right. What's more important is the method of modeling. And here we're using maximum likelihood. Now, maximum likelihood would try and take the distribution of your unknown variable. So here, our unknown variable is our YT. So we're trying to predict tomorrow's price, but we don't know what it is. It is an unknown. Therefore, we're trying to look at it as what we call a stochastic variable. Stochastic means that it changes with time. It doesn't stay the same, and it can be a bit random. There is maybe some method to the randomness, but there's some element of randomness in there. And there is a probability distribution that we like to talk about called the normal distribution. For example, most people tend to be of a specific height, the average height, and then from that height onwards, only a few people are a bit, actually for you it's the other way around, only a few people are a bit smaller, and a few people are a bit taller, and a few people are a bit smaller, but then it kind of trails off. So you have like a peak, and it kind of trails off like this. You have some people that are very, very small, and it just trails down. And the same the other way around. You have from the peak of the average height, it goes down, it goes down. You have some people that are a bit taller, a bit taller, a bit taller. But then you have some people that are extremely tall, but there are very few of them. And you see this, forms this kind of bell curve in its distribution. It turns out that you can figure out the probability of someone being a specific height. So if I was to ask you, what is the probability of someone being 2 foot? Well, this is something you can actually look at with this function right here, which is called the normal distribution, the normal function. Obviously, if it's 2 foot, it's quite low. Therefore, the probability is extremely low, but it's not 0. It's just very, very low. So if you have a look at this here, you have our function. Now we have pi in there. We have a square root. We have this little thing here, which is a sigma, which represents the variance. So, for example, let's say if we were to look at Nordic countries, they tend to have a higher variance in terms of how tall people can be because they're just more tall people. Whereas if you were to look at maybe some other countries where the average height is a bit lower, you'd have actually a higher variance because the peak would be lower, but there'll be just as many people. Let's say we're picking 2 countries with the same number of people. If you have a lot of people that are the same average height, then you'd have a very low variance and a high peak. But then if you have a high variance, you can have a lower peak if you have the same number of people in the 2 countries that I'm comparing here. You can do the same thing with stocks. Let's say you pick a stock and you think that the stock is most likely to be, let's say, $10, but you think that there's a low likelihood that it's going to be $11, and an even lower likelihood that it's going to be $12, and even lower for 13, and you can go the other way around, even lower for 9, 8, 7 dollars. And this is where you get your distribution from, and this is where you get your function. What you're trying to do here is that you're trying to take into account every single possible probability, and that's what we're doing right here. There, you see what we're doing is that we are multiplying. This is what this big pi does. We're multiplying every single possibility within this curve, within this probability function. And by doing this, by multiplying them, we are taking into account all possibilities, all permutations. And the reason we're doing this is because then if we were to plug in a value, if we were to say, okay, I'm looking for someone who's 6 foot, or I'm looking for the price of my stock being $10, we can then calculate how probable that's going to be according to our parameters. And our parameters here are going to be, if I scroll back up, in our ARMA model, is going to be our past values. So now what I can say is I can try and pick the probability of my dependent variable, which is YT, my stock price. I can try and pick the probability of that being correct as possible according to my past variables with the highest degree of precision, of accuracy, actually, not precision, of accuracy. And you can do this with the method I've just spoken about, which is to say, looking at the probability functions. So then we're multiplying them together to get the likelihood. So what is the likelihood of getting a specific amount? And this likelihood, we're just going to take the log of it. Don't ask why. The reason we're doing this is because think of it like mapping. We're mapping quite a complex structure, and then we're taking the log in order to be able to do quite a lot of kind of neat mathematical trickeries. It's really just a trick that we're doing here. We're taking the log just to be able to manipulate the data. And once we take the log of it, we call that the log likelihood function. Now, the reason there's a t here is because the log likelihood function for your parameters will change according to how many data points you've got. So here, t may be 1,000, then I think the accuracy would be a bit better than if t was 100, right? And then omega here are all of your parameters. And for an investigation into a probability distribution that is normal, we're only going to be looking at the mean and the variance. So if you remember, I spoke about that curve, and I said you can have a low variance and a high mean, or a lower mean and a higher variance if you have the same data distributed differently. The reason it has to be like this, and you can't have, for example, a low mean and a low variance as well, is because you are bounded by your parameters, by the number of data points that you have within there, unless then it gets so flat that it just becomes completely low. All right, so the normal distribution is parameterized within its mean and its standard deviation, and this is what we're seeing here. So you've got standard deviation right there, and we have the mean right here. By the way, standard deviation is just the square root of the variance, just FYI. So now that we have everything, we've taken the log. This is the log likelihood. Now we can just take the sum. Now, as I said, this is just a little piece of mathematical trickery, and we're continuing with this little piece of trickery in that we're taking parameters away, we're simplifying them, and then we're getting this function right here. Now, if we know where the variables are, if we know where the parameters are, if we know where the mean is, if we know where the variance is, then it's quite simple. You just stick it in and then have a look at what the most probable outcome is. However, we're going to go ahead with the assumption that we don't know what it is. We're going to estimate the mean as the expectation, which is to say just the mean of the observed variable we have this far, and same with the variance. So we have all of our parameters, which this time does not only include our variables, which is to say c, phi 1, 2, 3 up to p, and then psi 1, 2, 3 up to q, but also our variance. We're just pretending that we don't know what it is this time, and we're moving forward from there. Again, we're doing a bit of mathematical trickery. This is just continuation of the mathematical trickery that we're doing. You see there's quite a lot written, and the reason is because I wanted to show you everything step by step. I wanted to miss no steps. You'll be able to see what I'm taking, and I even write down in the article what I'm doing step by step. So this is the whole explanation of the mathematical trickery. I'm using some, again, some math know-how called the chain rule here, and then we're getting what we call our first order conditions. What we're doing here is that we're using calculus, which is to say we're just deriving our log likelihood function with respect to each of our variables in order to try and find out the value that the variable should have in order to be most likely what we've seen. Let me repeat that. I'm trying to figure out what C, because it's here. Let me maybe for me I should zoom in. You can see here that I'm doing the derivation, so I'm doing the differentiation of the log likelihood function with respect to C. Remember, C is the little constant that we have at the front to show the intrinsic value of whatever stock we're looking at. By doing this, and I'm going to make it equal to 0, by doing this, what I'm doing is I'm trying to figure out what is the value of C that is most likely to fit my model throughout the past data that I have, because it is most likely not to change just for tomorrow. That's it. That's what I'm doing here. And I'm going to be doing the same not just for C. So once I make it equal to 0, then by imposing this optimality by making it equal to 0, then I'm now looking at my estimate. So before, C was a theoretical constant that was true. I'm saying that this is correct, C exists, and it is a specific value. I don't know what that value is, but it is a specific value. But now that I'm putting a hat on top of it, now this is my estimate. If it's got a hat, it's my estimate, and it may have a distribution, it may have variance and a mean of its own, but that's not quite what we're going to be looking into right now. And that's it. So I'm making it equal to 0. That's my optimization of C in this respect. And here it is. Here's my little C hat. And I'm going to be doing the exact same thing for all of my phi's. So if I have phi 1, phi 2, phi 3, I'm going to do it 3 times, phi 4 again another time, and I'm going to be doing it again with each one of my psi. You can see that it gives you a function for each psi. And last but not least, we're going to do the same thing for the variance, because again, we're not expected to know what the variance is, especially since observing variance is a very difficult thing. I can get into it later if you're interested. Don't hesitate to ask questions in the chat if you're interested in this. I can, veer off for you if you want. But these are, the amalgamations of all of our first order conditions. That's what they're called. First order because we've only taken the first derivative and not the second or the third. So why have we done all this then? Where does Python come into play? When does coding comes into play? Well, I really like Sympy because it was amazing at actually showing you all of the maths. So here I've just clicked on it, and this is the library itself, its own official website, and it goes through logic, some linear algebra. I know it goes through some matrices. It even does some optimization for you. Now I decided not to use it because I wanted to do some actual mathematical optimization with some derivations myself, but you can just go ahead with something called the Newton optimization. It's funny, it's called Newton. He's not the one who came up with it. Nonetheless, it uses some of his techniques, so it's being called like this, and it's the most prolific in general. But yeah, you have some matrix algebra, calculus, solvers, basic operations. You can have a look at all this in on their official website. So now that we have all of this, let's try and get some data and apply what we've learned today. So first of all, let's import all of our Python modules, Python libraries, I mean. So I'm just importing sys here to show you what I'm working with, so Python 3.8.2, and things as such. And then I'm using Sympy version 1.6.2. Now you do unfortunately need to use that one. There's been an update that changed things, and I haven't had time to look at it yet to change my model. But I know that it works for this version of Sympy. Now that I'm here, now that we're starting the coding, I'm starting to think that maybe it's a better idea to go into a live environment to show you how you can actually start coding yourself. Now that's easy enough. All you have to do is scroll all the way up, click on the source code, and the source code is there for each one of our articles in the Refinitiv developer portal. And here you can just download the code. Now it's a zip file. You can download it onto your own PC, and then you can go on Codebook. So if you have Refinitiv Workspace, let me just show you how Codebook works. As soon as Workspace wakes up. Now, Codebook is available on Icon as well as Workspace. And all you have to do is go on the search bar at the top. There you go. And type code book, and it will come up. So I'm not going to reopen it because I've already got an environment opened with Codebook. And it's basically JupyterLab, but just an environment of your own in the cloud. So you don't have to go through any computing on your own PC, which may be problematic for some. All right, so if I was to scroll down now, this is going to be very slow in scrolling down and things as such. Reason being, there's an awful lot of math being shown, and that tends to slow down the actual scrolling itself, as you can see. But you can see all the mathematics itself right there. Is it a bit too small? Maybe let me try and make it into a presentation view. Yeah, let's do that. So that's all the math that we've seen before. That was all the mathematical trickery. That was a bit of a chain rule. Yep. If only it went a bit faster. There you go. First order conditions, and finally our code. Okay, so what we've done here is that we've imported sys, we've imported Sympy, which is version 1. I think 1.6. As soon as it's waking up. There you go. Oh, yes, in Codebook, you can't actually pip install libraries yourself. So the one that's already installed in there is 1.5.1. However, I've already run the code in there and it works fine. So you can run it yourself. Now, we have to set our P, our Q, and whether or not we have a C. Now, the decision as to whether or not you have C, so a constant in your model, is one that you have to take yourself. You have to look into your model and try and see if there is an intrinsic value into what you're looking at. That's up to you. So that's what we're doing here. We're setting up our initial arguments. So P and Q. So what do you think the lags should be? I know it's a bit strange to ask for you to figure out what P and Q is right now, but I'm just arbitrarily choosing them right now just to show you how it works. And then at the end, we're going to do what's called an ex ante. So before the fact, try and figure out what the lags should be. We're going to look into this at the end today. C, so whether or not there should be a constant at the start of your model. T, which is to say how many data points you have to train on. Let's say we've got 100. And this is simply just a list, a container in which we're going to be appending some lists in there. So here I'm giving you an example where we only have 6 data points. So T is 6, P and Q is 1, and we have a constant C as it's set to true. As you can see here, if C is true, I've let underscore C equal 1. Now I'm not going to go through all the code line by line, but I thought that maybe it would be interesting to show you the initial setup before we actually get into the meat of things. Here you can see how Sympy is used. We are going to create variables for each one of our, variables within our model. So here we have T, so the actual time period we're looking at, and sigma S. Now sigma S for squared, so that's what the S here stands for sigma squared. And sigma is basically our standard deviation, sigma squared is our variance. And again, if you remember, this is a variable that we're going to be having to estimate. So going forward, we're going to do the same thing again, but this time with y, and y is going to be a matrix of all of our observations being the price of the stock for the past however many days. Here we have a data set of size 6, so if we lose our first observations, because we're losing them to the model needs to see those lags in order to give you the first prediction. It's going to be 6 minus 2, I believe. Yes, PQ, and then you have C. So it's the maximum of P and Q, which is to say 1, and then the C. So we're losing 2 sets of observations. You can see it here, T minus max of PQ, and then minus 1. So going forward, here it is. Here, so now we have YT, which is to say YT minus 0, and we have YT minus 1 all the way up to YT minus 3. We can also do the same with our observations and let them be in a matrix, and the matrix will be X. So our matrix X is our matrix of observations, and then we can put everything together into our observation matrix, which is to say 1 for our constant, because this is just a constant, so it's going to be 1. Our past variables, so our price of the stock yesterday, 2 days ago, 3 days ago, 4 days ago, and also the model's error 1 day ago, 2 days ago, 3 days ago, 4 days ago. And we're going to go forward with this, having a look at the errors again. So we're going to have a matrix full of our errors and also a matrix full of our estimates. Estimates being C hat phi 1, because here's P and Q is 1, so phi 1 and psi 1. And altogether within omega, we're also going to include sigma squared. So sigma squared is something that we're going to try and estimate with our model. So here all I'm doing in this right there is I'm putting all of my variables into a log likelihood function, just like what I showed you above, but this time instead of it being just linear, it's in matrix form. So here you see what beta is, if I can go up, this is what beta is. So beta hat, because this is our estimates. So it's C, phi 1, and psi 1, all hats. That's what beta here is. Let me make sure. So this is beta without a hat. So this is not the estimate. This is the true value, the theoretical true value. That's right there. However, we did leave the hat in there. It's not going to change anything to do with the coding. There's an I at the end right here, which stands for just the fact that this is a matrix in and of its own. And this is our log likelihood version. Log likelihood in matrix version, just like we've seen above, just with matrices. Here what we're doing is that we're just expanding that log likelihood with each one of the variables we have. So before it was in matrix form, and now this is just linear. And finally, we can get our log likelihood function which is x dash x. It's right here, x dash x to the power of minus 1 times x dash y. And this is the result that we had above from the first order conditions that we had. So if we move onwards, we can see. Takes its time. There you go. This is the model put together with all the matrices, and this is the same but with hats, which is to say with the estimates. And once we've done this, we can differentiate our log likelihood function to try and get, you see, d omega. So we're differentiating our log likelihood function with respect to each one of the variables that we're trying to estimate. And this is what we've got right here, a big matrix of all the differentiations. So this one is with respect to C, this one is with respect to phi 1, then psi 1, and then the last one is with respect to sigma squared. And then what you can do once you've got all of those, you can rearrange the equations and plug in the data that you have. This far, we don't actually have actual visible data to plug in. We just have, for example, the number of variables we have, which is 6. And we are implementing in the model, losing our degrees of freedom, so we've only got 4. Which is why you end up with these things right here. What we've done here is that we're solving our first order condition, actually the one that's on the screen right now, that top one, which is for sigma squared, and we are optimizing for sigma squared. So this, what you're seeing here, is sigma squared. We haven't plugged in values yet for past values of our stock price. So we don't have an actual just a number, but we have a function with respect to all other variables within our models. All right. So now what we can do is that we can set up the conditions whereby we can then start to predict our stock prices with the ARMA function, the ARMA model. The ARMA model is going to be starting at the very start, the first prediction you're going to make is not going to be number one. Reason being, the first prediction you're going to make needs as many lags as you've got in your model. So if you've got an ARMA 2.2 model, that means you need 2 past values of data. So the first prediction you're trying to make will need the 0th value and the -1th value. But in our world, we count starting with 1. We don't count starting with -1. Therefore, we need to lose these first observations in order to get our first prediction. And that's what I meant when I said degrees of freedom. When you lose your degrees of freedom, you're actually losing these observations at the start in order to make your first observation, your first prediction with your model, your first estimates. And in order to do this, it needs to be, so you lose the first observations, which is to say P and Q, or the maximum between P and Q that there is, and then plus whichever observation you're looking at. So you lose, for example, if it's ARMA 2.2, you lose the first 2 observations, and then you do your first prediction. So if it's 2.2, you lose observation 1, you lose observation 2, and then you try to make observation 3, and then from 3 to 4 to 5 to 6, and you go onwards like this. When you make the first observation, so here let's say let's stick with ARMA 2.2 just to have consistent numbers. If we stick with 2.2, then this first observation that we're going to try and predict is going to be y3. And y3 is going to be including phi 1 and 2, as well as psi 1 and 2. And psi 1 and 2 is going to be with respect to errors of previous models. But here's the hiccup. We don't have previous models. This is the very, very first observation that we're having. And that's when we start to get into pseudo maximum likelihood as opposed to just straight up maximum likelihood. Due to the fact that we do not have observations for the errors, we need to assume that they are 0. You just assume that the first ones are 0, so your first 2 predictions were perfectly correct, and then from then on you start to include error into your model. And so the first observation here is one that tries to take into account errors being 0 in the past. Is trying to then predict what C is going to be. So this is our estimate of C. And then if we move on, so here's an example for an ARMA 1.1 model where you're trying to do this. C, your epsilon would be 0 and C would be 0, which is perfectly fine. This example I've just given was in scalar terms, which is to say matrices. And this one here is instead with matrices. So here it is. You've got your matrix. We are assuming that the errors are 0. So here you see we've got all of our errors. I'm substituting them with 0. So we only end up with 1 right here. So then, as per our previous equation, we can just lose. We can lose this one because here we don't have any hats anywhere. We're not predicting anything. This is the theoretical perfect model when we've assumed 0. But now, if we have our actual model, the one that we're actually predicting, we can put hats on top of our estimates, and we lose that error term because the error term is just not there anymore, thanks to the fact that we're just assuming that this is correct. So this is our actual model prediction, and this is not the model prediction, this is the actual model realization. So once you add the error term in there, this is the realization of the model. If you remove the error term, you have to put hats on top of everything because now you just are looking at your estimates, and within your estimates, you have an error, an inherent error, but that's not taken into account into your model because obviously you can't do that in advance. You don't know what your error is going to be in advance. If you did, you wouldn't make a model. You'd know exactly what the future holds. So moving forward, then we can just instead of writing massive matrices like this, we can just for example, y hats being all of our matrices about y hats, and we can let x be the matrix of all of these things, and beta be all of these things. You get it. We just compact everything into smaller variables to make it more understandable. And then once you've got the prediction, you can take one away from the other, which is to say the prediction away from the observation once you've seen it. And this is your new error, which you can use in the next model prediction. Now, I've spoken a lot about maths, but what about the actual, down-to-earth usability of this? So here's what I'm doing here with an ARMA 2.2 example. I'm first of all getting icon data. So here I'm using the Python library icon. I'm using a little trick here so that I don't have to show you my app key, but it's still getting it from a text file that stands alongside my code. I'm authenticating myself to icon, and once I've done this, I can then download, well, rather install some libraries, including NumPy, Pandas, and Icon, and I can collect data using Icon, which is say ek.getData. And here I'm focusing on the S&P 500. You can do anything, I'm just focusing on that. And I'm going to try and predict price, so close price specifically. So this is what the field is for close price. I found this in the data item browser, which you can just type in here, and it will come up for you. And I'm looking at daily data, so frequency D, and these time periods, starting from 2018, ending in 2019, just for the kicks. Moving forward, this is just a whole lot of libraries there to plot. So I'm just going to be plotting some data. For example, here is the plot of our S&P 500 data for the time period that we're looking at. And moving forward, we're now going to be testing the stationarity of the data. So I've told you before, you can read about stationarity elsewhere. You can test the stationarity of your data and of your model with this code. And by all means, copy and paste it, use it all yourself. This is a test statistic called ADF, Augmented Dickey-Fuller Tests, and there are a few other tests. I also put the number of observations used, as well as the critical values. So this is what's most interesting to me. I'd like to see the actual test statistic and the critical values for different confidence intervals. So confidence interval 1, 5, and 10%. So that's what I'd like to see in order to be able to make sure that my test statistic is higher or lower in order to figure out if it is stationary. Here we can see that it is not stationary, and that's not surprising at all. When it is not stationary, what we usually do is we take the difference, the first difference, and that's what I'm doing here. There you go. So here I've got my first difference, which is 1D of price close, and then I do a little test with augmented Dickey-Fuller, and I can see this time that indeed it is an awful lot smaller. So within the 1% confidence level, I know that my data is stationary. What does that mean? It means that now I can actually use this data in my ARMA model. Okay, so going forward then, now that I'm happy with my data, I can construct my first Y matrix. And the Y matrix is going to be the price of, so this is an ARMA 2.2, so it's going to be the price of the model yesterday and 2 days ago. So that's what it is right here. And I can also construct my X matrix within the model. If you remember the model with the log likelihood function, we need Y, we need X, and we need beta. We know X because it's just past values and also past errors. So if we don't know the past errors, we just assume them to be 0. That's why it's quasi maximum likelihood as opposed to just straightforward maximum likelihood. So we can construct our X and Y matrices, and that's what we're doing right here. And finally, we can construct our first order condition quasi maximum likelihood estimation of beta, and that's what it is right here. This is why it's called beta hat, because we're putting a hat on top of it because it is our estimation, and that's what it is right here. So it's x dash x to the power of -1 times x times y. So that's the very simple, straightforward maximum likelihood estimation. It's also the same as the ordinary least squared in this specific instance, just for you to know. Finally, I can create my new. Now that I have my new model, I can compare that modeled prediction with the observed variable, the observed price. And the difference between the two is going to be my first or my new error term. And now I can use that error term in the next ARMA iteration model that I'm doing. So this is going to be epsilon 4, so the fourth, because remember, it's ARMA 2.2, so the first two values we're losing. We've predicted the third, and now for that third model, we have an error term. So it's the error term for the fourth model, which is why it's epsilon 4. So this is the fourth epsilon, SPX for the S&P 500, SPX epsilon 4, and it happens to be -23. Now that's quite high, I think, but you expect it to be actually quite bad at the start, and then iteratively get much better as you go along. There's a little bit of a important notice about invertibility, which we need to take into account when we've got very little data. All right, I'm doing here the same thing again, but in scalar terms, just to show you all the mathematics so that you don't have to only use matrix algebra. But going forward, though, at some point, I'm going to just stop using scalar mathematics and just go straight for matrix one because it just becomes a bit messy. By the way, you might be wondering why this time we had actual numbers, right? The first time we didn't have numbers, we just had our estimate in terms. It was like this actually. We had our estimate in terms of other variables. So we have, variable y1, variable yt, y2, and everything is within these variables. But what I've done this time is I've used the first difference close price, this data that we've collected from Icon, and I've plugged it in. And that's when we got our y value, which is our prediction, but more importantly, our epsilon value right there. So this one is the third one, epsilon 3, with minus 7.9 being our epsilon error term that we can use for the next ARMA step. All right, going forward, if this was to wake up, there we go. We can continue to step 2 with matrix terms. So this is the same thing again with matrix terms, and now we have our epsilon 5. And then we can continue. This is an iterative process, and you do epsilon 5, so now you do the same with a matrix. You've got our S&P 500 data. We get our third y and x matrices to get our sixth epsilon value, and we continue like this. And this is quite simple to generalize. So now what I've done is I've taken all of this code and I've basically just put it next to each other. There's a few little quirks that you need to put in. For example, here I've rewritten some logic to do with whether or not you have a constant in your model. All you have to do is remove or keep the line of ones in your X matrix. As a matter of fact, if I go down, I think that's what you're going to see. No, I didn't write it down. But you've got your past observed values, which are right there. So it's S&P 500 first difference close price. And notice here it says m plus 1, because in mathematics, we start counting at 1, which is quite normal. But unfortunately, in inverted commas, in Python, you start counting at 0. It actually makes an awful lot more sense counting from 0, believe it or not, when you go 0, 1, 2, 3. Reason being then, if you start to do some mathematical manipulations with arrays, so data arrays that start at 0, it makes an awful lot more sense. Instead of doing times 2 and then at the end adding 1, which you would have to do if you started counting, or removing 1 as a matter of fact. If you're starting from 1, you can just do it straight away if you start counting from 0. So just to keep that in mind, I've let the y values and the x values be mathematical values, so they start counting from 1, and I've let all of these ones that have underscores in them be the actual observed Python floating point numbers, and they start at 0. So it's m plus 1, all the way to m plus p plus a. A, I think, would be the permutation. So step A, step 1, step 2, step 3, because we're iterating through each model prediction. A, and then just the minus 1 at the end again, which we don't see here because we're counting from 0. All right. Moving forward then, we have our generalized Python workflow. And what we're doing is that we're taking into account both a model with a constant, so the one right there with a 1 at the front, and a model without a constant. Not only are we looking at the mathematics, so having y and x's, but also the actual values, which is, say, SPX, first day close price. And we're constructing our matrices for each permutation. So this is a permutation with no constant, this one with a constant, and again, same here. This was for the first x, and then the first iteration. Then the second x, we're going to be doing the same thing again, with and without a constant. Third x. Okay, you get the idea. Instead of continuing with the two possible cases where you do and when you don't have c, your constant, in there, I'm just going to ignore the one when you do not have c because it's less complicated. And I've focused on the more complicated one of the two topics just to make sure that we cover the most complex case. So here we've kept 1 at the front. And notice here that we now have our epsilons, so our errors, and at the first, so what is this? So this must be ARMA 1.1 or something as such model, because we only have 1, 0 here, you see. We're only assuming that the first model has no errors. So we have ARMA P1. That's what it is. So we're moving onwards with all of this, and we've got all that, and you can see that it's actually I think it must be a square here, if I'm not mistaken. So this part here must be a square, and I think also that this part here must be a square. Do tell me if that's not quite correct, but it doesn't matter much anyway, because within the mathematics you have to multiply with each other. You have to square the matrix, so it's always going to be a square. So that means that you don't have to have any complex matrix manipulation later on. So this was just a whole lot of matrices, a whole lot of numbers put into the right place within the matrix, so that then you can go forward with the algebra. And believe it or not, that is really the main bulk of what you need to do. Because once you've done this, all you have to do is apply the maths that we've made this far. And in order to do that, let me just scroll down. We are going to look at all scenarios of ARMA models, which is to say one where you've got ARMA P0, so it's more of a AR model, an autoregressive model, rather than an ARMA model. MA standing for moving average. We're also looking at the ARMA P1 model, which is a bit different from the rest in terms of the matrix construction. And finally, the ARMA 1Q model. Now, you may be thinking, why are we not looking at the ARMA 0Q? And that's because it gets quite complicated, and there's also quite a few, Python libraries out there that you can use already to go through all of that. Okay, so these are the ones that we're going to go forward with, and we're generalizing the steps that we've gone through before. So I'm not going to go through all the steps again with you, but I have written them down step by step so that you can have a look at all the data. And that's what we're doing here. You see here we've got, instead of it being a Sympy matrix, which is quite lengthy to show, this is why it's really slow to scroll, is because I'm using Sympy matrices. Instead, I'm just using lists. And you can see the list of the data that we've got and the data I'm using before then applying the model that I'm looking at. So here is a model of ARMA 2, 1, because P is 2 and 1 is Q. And also I'm allowing for a constant, so I'm saying that C is true. And I'm going forward. And this is exactly what we've just been talking about all this time, but just applied into one cell, into one function. However, you'll notice, if I just go through this, that you can't have arbitrary lags here. What this means, if I scroll down, you'll see the graph. There we go. So this is the graph of our model. Now, I don't expect the model to be any good because I didn't look into the exogenous variables maybe that I should add. Maybe I should add into the model the GDP of the country. So here I'm looking at the S&P 500. So maybe I should look at the GDP of the US. Maybe that's correlated with the S&P 500. Maybe I should look at stimulus packages that were done during COVID times, which is quite recent. Does that change things? Now, these are all things to take into consideration. And these are exogenous variables that I've not included into my model, and I've also not looked into the number of lags I should use. So here it's like the maximum lag here is 2. Maybe I should use more, maybe 2, 3, 4, 5, 6, 7, 8, however many you want. The issue here, though, is that maybe I'm looking at a cyclical pattern. Maybe there's actually only something that happened last week on the same day that's interesting for today. If we look at only business days, then I'd be looking at 5 lags ago. So if I'm only looking at data that happened last Monday, I should not be looking at data that happened yesterday, the day before that, all the way up to 7 days ago or 5 business days ago. I should ignore the first 4. And that's actually quite tricky to do. Those are called arbitrary lags, and you can put arbitrary lags into this autoregressive moving average model. And doing this with the matrix construction I've showed you is possible, and this is what's going to be in part 2. So this is the end of part 1, and I'm hoping that by the end of the year I'll have the time to construct the whole thing. It happens to be that I've already written quite a substantial piece of it. Now we're not going to see it today, but that's going to be the topic for the next Twitch stream next week at 4 p.m. on Tuesday. So it's every Tuesday at 4 p.m. And then the next one, you and I are going to be coding together to try and put all of these things together, but not with compulsory past lags, but with just arbitrary lags going forward. All right. I can't see any questions in the chat. Maybe I went a bit too fast. Maybe you can go on the Q&A page on the developer portal. I would also like to apologize for the green screen. That seems to have left a gray shadow behind me. That's because today there's not much light and I can't really help. If I put light in front of me, it makes it even worse somehow. But this is where we're at. I hope this was useful for you. Next, we're going to be looking at how to figure out the number of parameters you should use. So what should P and what should Q be? And also, as I said, we're going to try and put everything together into one big Python function that does everything for you with arbitrary lags. But also, and more importantly, I think, it would also spit out the mathematical equations themselves. And you'll be able to see what is x, what is y, what is the maximum likelihood, not just the amount, because that's also given in most Python packages out there. But what is the equation? What is the equation that's been used here? What is the dimension of all the matrices that were used? And how did you come to the conclusion you came to? What I was really impressed with all this, I did all of this, and once I reached that level, I thought to myself, this is going to be way too much. 200 observation points, 7 columns, so however many arguments I was looking at, however many estimates I was trying to make. I thought that Sympy was very good at showing equations, but not very good at computing. Well, I was wrong. It computes very, very well, just as well as NumPy or things as such. I think that's what it does actually. It just takes a matrix, which you can, in its own engine, can do some matrix algebra. But then if you try to actually compute, I think it just transfers it to NumPy and then just does some array mathematics, which you would do normally in Python, and it does it for you, and it's quite efficient. All right, again, as you can see, no questions, so I'm hoping that means it was quite clear. And I hope to see you next week, and we're going to go together, trying to go forward with a function to make all this work. All right, have a nice day.